Good afternoon. So today I would like to share with you guys the idea for a scalable, robust, and mutually verifiable billing solution for the cloud computing. And we will first take a look at the trust issues in the cloud, and basically we will present BitBill. So more and more companies are using cloud computing. This is because it's easy to manage and easy to scale up, and it will require very small initial investment. But efficient and secure and correct billing for the cloud is still a major issue, and this is because of the underlying trust issues. For example, from the cloud service provider's perspective, they mostly worry about did I undercharge the client, and this is because there are some type of resources that cannot be measured correctly, and the cloud service provider will worry whether the client has used more than the service level agreements. And from the client's perspective, he mostly worry about did I overpay the provider? Did my payment did my usage justify my payment? And basically, in fact, 61 or more percent of the IT executive have listed pay only for what I use as the most important perceivable benefits of using cloud computing. However, these current billing solutions, as we will see later, cannot actually provide this benefit. And with these trust issues in mind, let's look at the current trust models in the cloud computing. We'll introduce both from the industry's perspective and the academia's perspective. First, let's look at the industry. Basically, there's only one trust model that is used, that is unconditional trust. The users will just trust the service provider will correctly calculate the usage and bill according to the agreement. This has very obvious drawback, is that the tenants has no bargaining power after they sign the contract. And even if their usage cannot justify their payment, they have no bargaining powers to try to adjust the contract. For this problem, actually, the academia has come up with several approaches, but they all center around the other trust model, which is the third-party trust. What they introduce is an authority that can verify the transactions between the tenants and the service providers, and the billing from the provider to the tenants will be verified by this trusted third party. And this approach also has some drawbacks. The first one is that the current solutions are all centralized approaches, and this introduced two things. One is it is a central point of failure for this central verifier. It means that if this central verifier goes down, the entire billing procedure of this cloud network cannot continue, and this is a big vulnerability. And the other one is it will become a congestive hotspot. With the increasing number of cloud tenants, the link between the tenants and provider to this verifier will become very congested, and this actually provides a bottleneck for the scalability of the cloud. And last but not least, it also assumes the trustworthiness of the verifier. And basically, now the tenants and the providers both trust this verifier unconditionally. And if there's, let's suppose there's a hacker that can impersonate such a verifier, this will actually introduce a very huge consequence. So. The problem, what we want to define is what is a good billing solution for the cloud, and we have identified these three major features. The first one is mutual verification. The billing have to be agreed by both the tenants and the service provider. And the second one is that the billing system should not be a bottleneck for the scalability of the cloud. That's why a centralized solution might not be that useful in this case. And the third one is the robustness. We do not want the billing system to be the vulnerability point or to be the weakest link in the entire cloud network. So, so our proposal is a very intuitive one. We want to involve both the tenants and the provider in the billing process. They will try to maintain in a P2P manner a single global history that is that they maintain and they verify, so that this single history can act like a global ledger. And basically, what we are proposing is a public trust model. So this is the trust model that we propose that is different from the unconditional trust and the third-party trust. In this trust model, no single entity is trusted unconditionally, but we make the assumption that the majority of the network, the majority of the nodes in the network is honest, and in this model, the tenants and the provider will form a P2P network that will maintain a log of billable events. With this single piece of history, global history, the billing is very intuitive. We just look at the items in this history and build the usage of the tenants accordingly. And each log of these events that constitute this piece of history is signed by the corresponding node, and it will be broadcast to the entire network so that the full history of the billable events are known to the BitBill network. And but there is still problem with whether when there's a malicious node, what do we do to prevent it? And basically, this comes down to the problem of keeping a global state in a untrustworthy environment. And this is actually the Byzantine general's problem that Bitcoin has solved very elegantly. And inspired by the Bitcoin approach, we will try to explain how BitBill works in a cloud billing context. And first, we will introduce a centralized solution to solve this problem. And then I will briefly introduce the Byzantine general's problem, and then present a distributed way to solve this problem. So for the centralized solution is basically based on a timestamper, a centralized timestamper. What you do is that it represents the global history as a chain of blocks, and these blocks contain billable items. This item represent the resource usage of different nodes. And basically, these times, when the nodes collect a set of items into a block, and it put a timestamp on this block, and this proves that the log item inside the block must have existed before the timestamp. And since each timestamp will be, since each block with timestamp will be hashed, and this hash will be included in the next block. So this will form a train of blocks, which represents the history of this network. And with each additional timestamp, it will reinforce the previous history of the block and basically endorse basically indicates the acceptance of the network to the items in that block. So this in this way, we can have a single piece of history, but this is actually maintained by a third party. What we want to do is that we want to eliminate this third party and distribute this task into the network. And how do we do this? And this is basically the Byzantine general's problem. Is it basically like this? We want to reach an agreement, in this case, the global history, a single global history, with a possible existence of the malicious nodes. And in this network, the peers send and receive messages to and from each other and try to reach an agreement. And the backstory of the Byzantine general's problem goes like this. the Byzantine is surrounded by several city-states, and the city-states each have a general that want to attack the Byzantine at the same time. So they have to reach an agreement on which time do they want to attack, and they try to negotiate by sending messengers to each other, and. Unfortunately, in these generals, some of them are working with the Byzantine Empire, and they actually want to confuse the other generals. So one possible way to sabotage this agreement is that some of the malicious generals will try to agree on multiple times. So that the honest general will go to attack the Byzantine Empire at different times, so that this general will be defeated, and Bitcoin actually solved this problem by a very simple, but in hindsight very simple, but it's actually a very elegant solution. But it is to add a cost to the announcement, to add a cost to the messenger. So before every general can send a message, you have to calculate a very difficult mathematical problem, and the message have to go with the message have to be accompanied by this solution to this problem, and the receiver of this message will first try to verify this problem, and we try to verify this problem before it accepts this message. And the problem is specifically designed so that at any single time instance, there's only one possible announcer of the in the entire network. And recall to the previous slides. We have a centralized timestamper. In this case, the general or the node that have the right to publish its message will be the timestamper of that time instant. So let's look at how BitBill implement this. We actually like the timestamper to be decentralized, and this is actually called the proof of work technique. The proof of work is a solution to a difficult mathematical problem, and in this case, our problem is that we want to find a random number that satisfy a special property. This property is that with this random number, the hash of the block, the starting 5 characters will be 0. So this is clearly an NP-hard problem. It is difficult to calculate. We can only calculate it using brute force, but it is very easy to verify. You just calculate the hash and you look at the first 5 characters. And this adds a cost to the announcement because everyone have to do this work and send this proof of work along with the message, along with the block of item that you want to publish as a timestamper. So this actually creates an insurmountable difficulty for the malicious node to announce to send out their messages. Because if we want to create its own history, you have to redo all the proof of work in the previous blocks, which any single node cannot be able to handle it unless it has the majority of the computational power in the network. So let's summarize how the BitBill network will actually operate. It will be. We first assume that each VM will have a BitBill module installed, and there is also a BitBill module installed in the domain 0 hypervisor, which represent the provider. So every new usage log will be broadcast to all the nodes, and the nodes will collect the usage log into its own block, and will try to find a difficult proof of work for its own block. And then when a node finds a proof of work, it will broadcast the block to the other nodes, and the other nodes will try to verify this proof of work, and then accept the block only if all the logs inside this block is valid. And the nodes will express their acceptance to the block by working on the next block in the chain using the hash of the previous block that they have just accepted. And in this case, the the existence of the log items is actually very important. We are using a Merkle tree to store for efficient storage and the verification of the items. We choose Merkle tree because they have a very special property. Every non-leaf node is labeled with the hash of the labels of its children. So to verify item, we actually need to find a block header of the longest chain, which is the most trustworthy history in the network, and we obtain a Merkle branch linking to the transaction to the block that it has timestamped in. In the example on the right, we are actually verifying item 2 through the Merkle root that is located in the block header of that transaction. So actually, the existence of the block item means two things. The first thing is that for the block that is located in, it means that there is a network node that has accepted this transaction. And the second meaning of this log item is that all the following blocks indicates that the generator of these blocks also accepted this transaction because it has included this transaction in its own hash. But basically, the longest chain is the most important, is the most trustworthy history. Is just because of this, because the largest number of nodes have endorsed this history. So BitBill actually does one thing and one thing only, that is to maintain a trustworthy billing history. It's a global ledger, and this is important to guarantee the correctness of this history, and we let the nodes to identify and resolve these conflicts. And the verification is based on very simple rules. That is, the basic principle is that a single piece of a resource cannot be used twice by multiple tenants. For example, a CPU cycle cannot use concurrently by 2 tenants. Instantaneous bandwidth cannot exceed the link capacity, and the aggregate memory usage cannot exceed the physical limit. And using this very simple rules, validation rules, the nodes have the ability to identify the conflicts and can try to resolve it. And basically, we are currently working on the algorithms to implement these verification rules. So, despite the advantages of BitBill, we are interested in knowing the resources we need to enable BitBill, and does this resource justify its cost? So, we categorize the influence factors on 2 aspects. First is on the end host. And we need to know the frequency of broadcast, the difficulty of proof of work, and the granularity of the event collection, and for basically granularity of the sampling. And on the network side, we need to look at the number of nodes and the frequency of the broadcast. Actually, the frequency of the broadcast is directly related to the difficulty of the proof of work. If we have a very easy proof of work, it means that the solution is very easy to find. And once we find the solution, we make a broadcast. And this is actually the central trade-off in the resource consumption of BitBill. If we want to have if we want to reduce the load of the BitBill module, we are actually decreasing the difficulty of the proof of work, but in the same time, we are increasing the load on the network because the frequencies will become higher. And if we want to reduce the load on the network, we can reduce the frequency of the broadcast, but in the same time, the difficulty of the proof of work will become will increase accordingly. So. We can look at the graph on the top right, which is the computational difficulty. In Bitcoin, they basically the entire network will try to output 1 block every 10 minutes, and by reducing the difficulty in BitBill, we can reduce it down to 1 minute. But we still think that we can decrease this more, because for data center, the RTT is always in the less than a few hundred microseconds, which is very compared to the minute, it will be like a century in the data center network. So we are looking at decreasing this. But in the same time, decreasing this means that we need to increase the load on the network. So this is another trade-off we need to look at. And the graph on the bottom right actually describes the scalability of the BitBill network. We are comparing with a third-party trust model that. We are looking at the occupancy, the link utilization, and the critical link. Since we have distributed the timestamping of the BitBill, and we can actually in BitBill network there is no critical link because it's a peer-to-peer network. And when we scale the number of VMs in the network, it will actually prove that we have a much better scalability than the centralized third-party model. So actually, there are some interesting problems that are related to that are the implications of BitBill. The first one, you might be interested in the privacy. Basically, the tenants might not want to disclose their usage, their performance usage, their resource usage. So we think BitBill can deal with this problem by decoupling the public key with the identity. We can only associate the resource usage with the public key, but we cannot associate the resource usage with the identity of the tenants. And in this case, we create a privacy protection for the tenants. The other issue is deployment, and we think BitBill should be a software package pre-installed by the service provider or by the tenant itself. And and the correctness of this package can be verified by the hash of its own package. Basically, the tenants can check the correctness of the package that is pre-installed by the provider to ensure that this is actually the correct package that can correctly participate in the BitBill network. Another important issue is granularity. Is the resource monitoring, the granularity of the resource monitoring. And as we discussed in the previous slides, it actually impacts the load on both on the network and on the client itself. So and this is the area where we are currently looking at. So in summary, we have classified the current trust models in the cloud and propose a new trust model that is called public trust. And we deal with the Byzantine generals problem that comes with this model using a Bitcoin-like mechanism. And we design a scalable and robust peer-to-peer billing accounting solution called BitBill. Yes, thank you. I would like to take some questions. Thank you.
Questions? I think the technology is kind of sophisticated. It's difficult to follow all the reasoning through it. What is the sort of interval at which resolution of the billing and accounting needs to happen? How many people need? I understand that you have a record that is verifiable.
Yeah.
But how often does it need to be verified? How does the entire checking process work?
Well, it actually depends on the billing period of the service provider. It can be 1 month or 1 week, and after 1 month, and the history will be wiped, and we start a new process. And after 1 month, we can start billing again, and then just wipe the previous record, and then go on to the next month. It actually just depends on the how the provider would like to charge the tenants.
Right, because there's still there's always opportunities for creating fraud.
Yes, yes, sure.
Until someone actually does the audits.
Actually, we want to prevent that. Since we want to provide a trustworthy model, we assume that all the honest tenants will try to filter out the false records by themselves using the validation rules that we just described. So that the entire history is at least is considered correct by the tenant at that time. But if there's other problems, then we can deal with it when the billing comes.
Or a dispute.
Yeah. So basically, now the tenant will have the record to dispute before they do not have this kind of privilege. They just sign a contract and they will pay whatever the provider has billed them.
Okay. Well, thank you very much.
Thank you.